In this lesson, we're going to continue to work with Maclaurin series, and we're going to focus on finding the Maclaurin expansion of functions that are a composition of a function that we already know, one that is familiar to us, like the exponential, the logarithm, the sine, and the cosine, and another function that is not as familiar. Let's begin by reintroducing some of the basic Maclaurin expansions that we should be familiar with. These can be found in your formula booklet if you ever need them. And if you want to check for them, then you can just follow the process to create the Maclaurin series that we discussed in the previous lesson and find the series by yourselves. Once you have done that and you feel confident, then all you have to do is just use the series as is given here. So the basic functions that you have to be familiar with are, of course, the exponential function, the logarithm of 1 plus x, sine of x, cosine of x, and arctangent of x. Like I said, these are available for you in your formula booklet. What are we going to do? So the point of this lesson is to guide you into how to find the Maclaurin expansion of functions that are combinations of these functions. For example, what if you have the function y equals e to the power of x plus 1? This is the function e power x combination x plus 1. So what we can do to get the expansion of e to the power of x plus 1 is to substitute or to do the combination of x plus 1 in the expansion of e power x. So what that would look like is basically we're going to interchange e power x with its series expansion. So it's going to be 1 plus x squared over 2 factorial plus x power 3 over 3 factorial and so on in combination with x plus 1. And what that means is we simply substitute x plus 1 instead of x. So 1 plus x plus 1 plus x plus 1 squared over 2 factorial plus x plus 1 power 3 over 3 factorial and so on. So in general, the function e to the power of x plus 1 is going to be the sum from n equals 0 to infinity of x plus 1 power n over n factorial. Let's consider another example. Let's take the function y equals natural logarithm of 1 plus x squared. So this function is a composition of natural logarithm of 1 plus x in composition with x squared. So what we want to do now is to take the Maclaurin expansion of natural logarithm of 1 plus x, which we already know, and do the composition with x squared. So when we substitute, we get y equals ln 1 plus x squared. That would be equal to x squared minus x squared squared over 2 plus x squared power 3 over 3 minus etc. So that means the expansion is going to be ln of 1 plus x squared is x power 2 minus 1/2 x power 4 plus 1/3 x power 6 minus etc. Now we can always combine two of these expansions to get a more interesting approach. So for example, in this problem, we're asked to find a Maclaurin series for the expansion of e to the power of sine of x as far as the term in x power 4. So the function that we're working with is the function y equals e to the power of sine of x. And we know that sine of x can be expanded like this. So we're going to substitute that expansion in the exponent of e power x. But because we only want the total expansion or the final expansion to be x to the power of 4, I'm only going to substitute the first two terms of the sine of x. I'm going to take an approximation of this series. So this would be e to the power of x minus x power 3 over 3 factorial. And now what I want to do is I want to separate these powers of x using the properties of exponents. So this is going to be e to the power of x times e to the power of minus x power 3 over 3 factorial. And what I can do next is I can use now the expansion of e to the power of x to expand each of these individually. Again, up to a certain power of x. I don't want to have terms that I'm not necessarily going to use. So I'm going to expand the first one as 1 plus x power 2 over 2 factorial plus da da da. So I'll write it first and then I'll decide how many terms I want. And then the second one is going to be 1 plus, and this is a composition of e power x with x power 3 over 3 factorial. So this should be minus x power 3 over 3 factorial plus 1/2 minus x power 3 over 3 factorial squared plus da, da, da. And now I can see that this term is already x to the power of 6. So from this expansion, I'm only going to keep these two terms. And from this expansion, because I need to get the x power 4 term, multiplying this one, I'm going to consider all the terms from x power 0 to x power 4. So this is equal to 1 plus x, and I'm going to approximate right away, plus x squared over 2 factorial plus x power 3 over 3 factorial plus x power 4 over 4 factorial, and that's where I'm going to stop. And then times 1 minus x power 3 over 3 factorial. And now let's multiply these two polynomials, and this is equal to So after simplifying all of that and dismissing the additional powers of x bigger than 4 that we found, then we get a 4-degree polynomial that approximates e to the power of sine of x and is given by this expression. Let's do one final example. In this problem, we are given the function ln of the square root of 1 plus 2x over 2 minus 3x, and we're asked to find the Maclaurin expansion up to the term in x power 3 and state the interval in which the expansion is valid. Just like before, the aim of this problem is going to be to substitute a composition into the expansion for the natural logarithm. However, this expression that we have inside is a little bit too complicated for us to do an immediate composition. So we're going to work this a little bit using the properties of logarithms and trying to simplify this to the best that we can. So let's begin with ln of 1 plus 2x over 2 minus 3x. Now we know that the logarithm of a quotient is the difference of the logarithm of the numerator minus the logarithm of the denominator. So using that property, this is the same as ln of 1 plus 2x minus ln of 2 minus 3x. Now I want to go ahead and write the square root as a power. So this would be 1 plus 2x to the power of 1/2, and then this would be ln of, and I want to write this in a way that I will be able to relate it to the original expansion. So I'm going to take the 2 out as common factor to get 1 minus 3 over 2x, and I'm going to separate that using the product rule for logarithms. And here in the first term, I'm going to bring the exponent down to get ln of 1 plus 2x multiplied by a half. So now let's separate this product, and this is going to be ln of 2 plus ln of 1 minus 3 halves of x. Now I'm going to break that parenthesis, and this is going to be 1/2 ln 1 plus 2x minus ln 1 minus 3 halves of x minus ln of 2. Now I'm going to work with these two functions independently. I'm going to see what the expansions would be. So I'm going to call this function function number 1. This is going to be function number 2. So for number 1, this is ln of 1 plus x in composition with 2x. So the expansion is going to be 2x minus 2x squared by 2 plus 2x power 3 by 3 minus etc. And this is 2x minus 2x squared plus 8/3 x power 3 minus and so on. Now function number 2, this is a composition of 1 plus x and minus 3 halves of x. So the expansion of ln 1 minus 3 halves x is going to be minus 3 halves x minus 1/2 minus 3 halves x squared plus 1/3 minus 3 halves x power 3 and so on. This is equal to minus 3 halves of x minus 9/8 of x squared minus 9/8 of x power 3. And at this point, we can dismiss all the terms that are beyond the x power 3 term. So we're going to dismiss anything in this region. Now we're going to just substitute back into the function, and that is going to be and now we have finished the expansion up to the term of x power 3. Now the second part of the question is state the interval or the values of x for which this expansion is valid. So let's remember that these expansions, the Maclaurin expansions, are only valid in the vicinity of 0. So in general, the expansion for ln of 1 plus x is valid around 0, like we said. It's for x between minus 1 and 1. So that would mean that for the expansion of ln of 1 plus 2x, 2x should be between minus 1 and 1 as well. And for the expansion of 1 minus 3 halves of x, then it's minus 3 halves of x, the one that should be between minus 1 and 1. So the second condition that we have here leads to x taking values between minus 1/2 and 1/2. The third condition that we have here leads to values of x between minus 2/3 and 2/3. So with these intervals in mind, we need to see the overlapping sections, and that is going to be x between minus 1/2 and 1/2.